Hey y'all, I'm in Maine and my daughter is going to be giving birth soon, and actually we're going to be having a blizzard coming up pretty soon. It's kind of revving up for it. As you can see, there's already a ton of snow, but anyway, things just seemed really iffy as to whether I'd be able to do Google Meet tomorrow, so I decided to go ahead and do a video, and I'm just going to be going over the notes that I gave you, and just want to remind you that you have a test next week, and your notes explain that. Your homework will prepare you for that. Just remember that is your last test of the quarter, and you need to do your very best to try to get ready for that. And if you have any questions during the week, please email me and I will help you out with that. So we're going to get started. Okay, we've got a lot to cover right now. So I'm just going to get moving, and we'll see what we can do. So I want to make sure that you know that on your test, you will not have to memorize all these identities and all these formulas in chapter 5. You're just going to have to know what you already had to know, which is the reciprocal identities. You have to know sine and cosecant are reciprocals, cosine and secant are reciprocals, tangent and cotangent are reciprocals. You have to know that. Quotient identities, tangent x is sine over cosine, cotangent is cosine over sine. You have to know that by heart. Pythagorean identities, sine squared x plus cosine squared x equals 1. And you have to know these two as well, but you can figure out those two just by using sine squared x plus cosine squared x is equal to 1. You can divide that whole thing through by sine squared. And that gives you 1 plus cotangent squared x is equal to cosecant squared x. So that is the third one. If you divide that first one by cosine squared x, you get the second one. So you don't have to memorize all three. You really just have to memorize the first one. And then you have to remember that you can figure out what the other two are. You do have to know that sine and tangent, and therefore cosecant and cotangent, are odd functions. So tangent is odd, cosecant x is also odd, cotangent x is also odd, and you don't actually have to memorize that these guys are odd if you just remember that cosine is even, because then you'll know. Besides secant, okay, secant goes with cosine. So secant and cosine are even. Now everybody else is odd. And then the cofunction identities, you need to know that cosine, remember cosine means sine of the complement. That's what that word means. So the cosine of x is just the sine of the complement of x. Cosine of x equals the sine of the complement of x, pi over 2 minus x. So this is what a cofunction is. It means it's the function that if you take the other function of the complement, no, that's too hard to say. All right, so just be sure that you know that sine pi over 2 minus x is cosine x, and tangent pi over 2 minus x is cotangent x. So those are the cofunction identities. Make sure you know those. Every other identity and formula you will be given on your test, and you will need to know how to use them, but you will not have to memorize them. Okay, section 5.3, we're going to have the double angle, power reducing, and half angle formulas. All right, so I'm just going to go through these super quick. I'm not going to spend a lot of time on derivations. I'll explain where some of them come from, and I won't explain where others come from. The double angle formulas for sine 2 theta, cosine 2 theta, tangent 2 theta, these just come from using the sum formulas for sine, cosine, and tangent. So the sum formula for sine is sine u plus v is equal to sine u cosine v plus cosine u sine v. So we can use that to find sine 2 theta, because we can just write sine 2 theta as sine theta plus theta. That's the same thing as sine 2 theta. Theta plus theta is 2 theta. So we just plug that into the formula, and we have sine theta cosine theta plus cosine theta sine theta. which is just 2 sine theta cosine theta. So for cosine 2 theta, we do the same thing, cosine theta plus theta, and we use that cosine formula for sums, which is cosine theta minus sine theta. So that's just cosine squared theta minus sine squared theta. And you can write that a couple of other ways that are useful sometimes. Cosine squared theta is the same thing as 1 minus sine squared theta, of course, because of the Pythagorean identity. So you can also write this as 1 minus 2 sine squared theta. And then also, of course, sine squared theta is 1 minus cosine squared theta. So you can also write this as 2 cosine squared theta minus 1. So there are 3 useful forms of that cosine 2 theta. Tangent 2 theta, you would do the same thing. I'm just going to speed through it. You can look at it in the chart right here, double angle formulas. So they're all listed there for you in your book, in your notes. And here's how you can use those to find sine, cosine, tangent of certain angles that relate to angles you already know. So if you are given that sine theta is 2 over 3 and theta is a second quadrant angle, then you're going to draw that triangle that goes with the angle theta. So you've got this angle theta, second quadrant. It tells you that the sine is 2 over 3. That means opposite over hypotenuse. So that's the 2 and the 3. And then if you use the Pythagorean theorem to find the other side of that triangle, you got the square root of 5. So now you've got all the sides of the triangle. You can find sine, cosine, and tangent for theta. You can find all the trig functions for theta. Sine 2 theta, we know, we just figured it out, is 2 sine theta cosine theta. And since we have the triangle, we can now fill that in. So 2 times 2/3, and then the cosine theta, if you look at your triangle, is adjacent over hypotenuse, which is square root of 5 over 3. Notice that cosine is negative because we're in the second quadrant. So multiply that out, and you're just going to get negative 4 square root of 5 over 9. And so that is sine 2 theta. And then for cosine 2 theta, again, you're going to use one of these formulas. We're going to use the second one because it's easier to use 1 minus 2 sine squared theta because we already know what sine theta is. So 1 minus 2 times 2/3 squared, and that's just going to be 1 minus 8/9, which is 1/9. And then to find sine 2 theta, we can actually not even use the formula because we know that sine 2 theta is going to equal sine 2 theta over cosine 2 theta because tangent is equal to sine over cosine. And since we've already found out what sine 2 theta and cosine 2 theta are, we can just plug those in. So negative 4 square root of 5 over 9 over 1 over 9. So the 9's cancel, and you just have negative 4 square root of 5 for tangent 2 theta. Okay, we want to verify the identity. Sine 3x is equal to 3 sine x minus 4 sine cubed x. Since we were just doing the double angle formulas and the sum formulas for sine, and we can see that we want all signs on the right side. We want just signs everywhere. We will just use the sum formula for sine. And to do that, we will just break 3x up into sine 2x plus x. So all we're doing here is just making 3x into 2x plus x. And that way we can use the sum formula for sine. So we'll just plug that into that formula, and we'll have sine 2x cosine x plus cosine 2x sine x. And now we will use those double angle formulas that we just learned. So sine 2x, we know, is 2 sine x cosine x. So we'll use that on that first part. So we'll have 2 sine x cosine x. And then we've got that other cosine x being multiplied by that. So let's write that right there. And next we'll do this cosine 2x, which is we just learned about, and we'll use the version where it's 1 minus sine squared x because then there'll be a lot of sines, and that's what we want. So cosine 2 theta is equal to 1 minus 2 sine squared theta. We'll use that. We'll have 1 minus 2 sine squared x, and then we've got that sine x sitting there at the end. We'll put that. And now we just need to clean this up a little bit. We've got 2 sine x cosine squared x And then we can use the distributive property here, sine x minus 2 sine cubed x. And so now we have cosine squared x in that first term, and we know that cosine squared is 1 minus sine squared by the Pythagorean identity, so we'll put that in because we want all sines. And once we do that, we're almost done because all we're going to have to do is distribute that 2 sine x and then add it all up, and it will look just like the right side of the equation. So 2 sine x minus 2 sine cubed x plus sine x minus 2 sine cubed x. And so we add it all up, and we have 3 sine x minus 4 sine cubed x, which is the right side of the equation, and so we're done. Okay, the double angle formula for cosine can be used to express the even powers of sine and cosine in terms of the first power of cosine. So one of those versions of the cosine 2 theta identity or formula was cosine 2 theta equals 1 minus 2 sine squared theta. If we solve that equation for sine squared, we get sine squared by itself in that equation, move it to the left, and then move the cosine 2 theta to the right. We're going to have 2 sine squared theta equals 1 minus cosine 2 theta. And then if we divide both sides by 2, and then you can see that you started out with sine theta and you end up with something that just has a first power of cosine. So sometimes if you have a sine squared or a cosine squared, you don't want that. You want to get something that's to the first power. That's what this kind of formula helps you do, these power reducing formulas. So here they are, power reducing formulas. You've got sine squared theta equals 1 minus cosine 2 theta over 2. Cosine squared theta is 1 plus cosine 2 theta over 2. And tangent squared theta is 1 minus cosine 2 theta over 1 plus cosine 2 theta. So we're going to use those to reduce this expression, sine to the fourth x plus cosine squared x, down to just first powers of cosine. So the first thing we're going to do is change sine to the fourth x to sine squared x squared. So we're going to square it. And then we'll have a cosine squared x right there. That's still there. And now we're going to use that formula for sine squared theta, and we're going to substitute that in for sine squared x in that blue set of parentheses. So we'll put that in, 1 minus cosine 2x over 2 squared. And then for cosine squared, we can use this formula right here. So we'll have 1 plus cosine 2 theta over 2. And you can see that in the blue parentheses, when you square that out, you're going to get a denominator of 4. And so you're going to want a common denominator here. So I'm going to go ahead and multiply that second fraction by 2 over 2 so that when I square out that blue set of parentheses, I'll have a common denominator for both fractions. So I'm going to square the first term, write it all out, 1 minus 2 cosine 2x plus cosine squared 2x all over 4. And then we've got 2 plus 2 cosine 2x over 4. So now we have the common denominator, and we can just add the numerators. And since we can do that, we've got a negative 2 cosine 2x up there and a positive 2 cosine 2x. Those cancel. And so we're just left on top with 3 plus cosine squared 2x over 4. And so now we just need to get that cosine squared 2x to be something to the first power. And we can do that because we can use that same middle power reducing formula up there. But now instead of just theta or just x for our argument, we have 2x, which means that when we use the formula, we're going to have to write here, it's going to end up being 4x because whatever that is always double whatever that is that you start with. The angle you start with, it's always going to be double in that cosine term. So when we write cosine squared 2x, we're going to have 1 plus cosine 4x over 2. So that's all we need to just pay attention to. 1 plus cosine 4x over 2. So 3 plus that over 4. And then if we're going to need to reduce this complex fraction because we have a fraction in our fraction. So the way I do that is I just multiply the whole big fraction by 2 over 2. I'm going to distribute that 2 through the numerator, so I'll have 6 plus, the 2's will cancel in the second term, and I'll have 1 plus cosine 4x all over 8. And then if I reduce that down, I've got 7 plus cosine 4x over 8. And if I separate that into two fractions, 7/8 plus 1/8 cosine 4x. So that is an expression that has just first power of cosine. It doesn't have any squares or anything. And that's what we were supposed to do. Okay, if we substitute alpha over 2 for theta in the power reducing formulas, we get the half angle formulas. So you've got this sine squared theta equals 1 minus cosine 2 theta over 2. That's what we got when we solved for sine squared in the cosine double angle formula to get the power reducing formula. So that's what that is. Now what we're going to do is we're going to substitute alpha over 2 for theta. So we're going to represent theta as some angle over 2. And that is going to give us 1 minus cosine 2 times alpha over 2 over 2. And that's going to give us sine squared alpha over 2 is equal to 1 minus cosine alpha over 2. And then if I take the square root on both sides, I'm going to have sine alpha over 2 is equal to plus or minus the square root of 1 minus cosine alpha over 2. So this is called a half angle identity because now if you have some angle you know, like 30 or 60 or 315, for example, and you want to know the sine of 15 or the sine of 22.5 or something that's half of an angle you already know, now you can do that using the half angle identity. And that plus or minus sign in front of the square root doesn't mean that it can be both. What it means is that it depends on what quadrant you're in. It depends on what quadrant alpha over 2 is in. If this is sine alpha over 2, if alpha over 2 is in the first or second quadrant, it's going to be positive because that's where sine is positive. If it's in the third or fourth quadrant, it's going to be negative because that's where sine is negative. So the plus or minus doesn't mean it's both. It just means it will be either plus or minus depending on what quadrant alpha over 2 is in. So looking at an example. So use a half angle identity to find the exact value of cosine 157.5. Well, you would imagine that 157.5 is half of an angle that you actually know. And if you multiply 157.5 by 2, you get 315. So you can write this as cosine 315 over 2. So now you have a half angle, you have an alpha over 2, and you can use one of these identities. So cosine 315 over 2, if you use that cosine identity up there, you're going to have plus or minus 1 plus cosine 315 over 2. And I put a negative sign in there because it's a second quadrant angle. 157.5 is in the second quadrant. And so that means cosine is negative because that's where cosine is negative. So that's going to be negative square root of 1 plus cosine 315, which is square root of 2 over 2, all over 2. And so I'm going to simplify that complex fraction by multiplying it by 2 over 2. So I'll have the negative square root of 2 plus the square root of 2 all over 4. And if I reduce that and rationalize it, I'm going to have negative 2 plus the square root of 2 inside the square root over 2. And so that is cosine 157.5. This is another derivation for the tangent half angle identity. You can see that in your book because we don't have time. So we're not going to go over that derivation, but you still will use that formula when you need it. All right, so there are the half angle formulas right there. And again, the sign is plus or it's minus depending on what quadrant you're in for alpha over 2. So don't think that you can have both plus and minus. It means just whatever sign it's supposed to be. So if sine alpha is negative 4/5 and alpha is between pi and 3 pi over 2, find the exact values of each expression. All right, so sine alpha is negative 4/5 and alpha is between pi and 3 pi over 2. So alpha is a third quadrant angle with a sine of negative 4/5. So opposite over hypotenuse, you can see it in the picture, is 4 over 5. We're in the third quadrant, sine is negative, and so there you are. In that quadrant, remember sine and cosine are both negative, and tangent is positive. So we need to be careful because those signs are on alpha. Okay, we're talking about sine alpha, cosine alpha, tangent alpha. Those things would have to do with the third quadrant, but we're not looking at alpha right now. We're looking at alpha over 2. So we have to think about what quadrant is alpha over 2 in, so we'll know what sign to put on our answer. So if alpha is between pi and 3 pi over 2, so if alpha is in the third quadrant like that, if we divide that inequality by 2, we're going to get that alpha over 2 is between pi over 2 and 3 pi over 4, which is in the second quadrant. So alpha over 2 is in quadrant 2. So we know that when we do part A, we better get a positive answer because we're taking the sine of alpha over 2. So make sure you're paying attention to what quadrant you're in, what quadrant the actual argument of sine or cosine or tangent that you're working on is in. So they told us alpha was in quadrant 3, but they only told us that so we could figure out what quadrant alpha over 2 is in. And it's in quadrant 2. So finding that sign, we just use the formula. I'm reminding myself that the answer is going to be positive because sine is positive in the second quadrant. And so sine alpha over 2 is going to be positive square root of 1 minus cosine alpha over 2. And I know that alpha has the cosine negative 3 over 5. It is adjacent over hypotenuse, and that's cosine. That's negative in the third quadrant, and alpha is in the third quadrant, so cosine alpha is negative. So we have square root of 1 minus 3, negative 3/5 over 2. And if we just add all that up, we're going to have 5/5 plus 3/5 over 2, which is going to be 8/5 over 2, which is going to be the square root of 8/10, which is the square root of 4/5. And if you get that 4 out from under the square root and rationalize that thing, you're going to have 2 square root of 5 over 5. For part B now, we're looking at cosine alpha over 2. Alpha over 2 is still in the second quadrant. It didn't go anywhere. And so it's going to be negative because cosine is negative in the second quadrant. So we need to remember that our answer for part B should be negative. So reminding myself of that, I'll use the formula for cosine alpha over 2, which is cosine alpha over 2 is equal to negative 1 plus cosine alpha over 2 inside the square root. And now we just plug in what we know. We know that cosine alpha is negative 3/5, so we can put that in and do all that stuff. And so we have negative square root of 5/5 minus 3/5, which is 2/5 over 2. And that's negative square root of 2/10, which is 1/5. And if we rationalize it, we get negative square root of 5 over 5. Part C, we're still in the third quadrant for alpha, so we're in the second quadrant for alpha over 2, and tangent is negative in the second quadrant. It's positive in the third quadrant, so we just got to make sure that our answer is negative. Reminding myself of that. Now I'm going to use the formula for tangent alpha over 2, which is sine alpha over 1 plus cosine alpha. And I know that sine alpha is negative 4/5, and cosine alpha is negative 3/5. And so I just add all that up, negative 4/5 over 2/5, which is just 4 over 2, which is 2. And it's negative because tangent is negative in the second quadrant. Okay, section 5.4, product to sum and sum to product formulas. In integral calculus, it's usually easier to work with a sum of trig functions than a product. So it's sometimes necessary to want to change a product to a sum. And so the derivations for the product to sum formulas come straight from the sum and difference formulas for sine and cosine. So for example, if we start with 1/2 cosine u minus v minus cosine u plus v, then we can get to the left side. So we're going from right to left. We can verify one of these formulas. So all we have to do is use the sum and difference formulas for cosine. So 1/2 times cosine u minus v, which is cosine u, cosine v, plus sine u, sine v, and then minus cosine u plus v, which is just going to be cosine u, cosine v, minus sine u, sine v. And you are subtracting those. And so you can see that you're going to have cosine u, cosine v is going to cancel out, and you're going to have 2 sine u, sine v times 1/2. And so the 1/2 and the 2 cancel, and you just end up with sine u, sine v. So that's where these product to sum formulas come from, and we are going to just go ahead and use them. So write the product as a sum or difference. So we've got sine 7x times cosine 3x, so we're going to use that sine u cosine v up there at the top. And we'll just plug those in for u and b. So we'll have 1/2 sine 7x plus 3x and sine 7x minus 3x. So that's just 1/2 times sine 10x plus 1/2 sine 4x. And for part B, we just can use the first sine u, sine v. So we've got sine is odd, so we need to go ahead and rewrite sine negative x as negative sine x. And then we can go ahead and use that formula. So we'll have 1/2 cosine u minus v, so x minus 4x, minus cosine u plus v, so cosine x plus 4x. So we're going to go ahead and distribute the negative 1/2. So we're going to have negative 1/2 cosine negative 3x plus 1/2 cosine 5x. And since we know that cosine is even, we can just rewrite negative 1/2 cosine negative 3x as negative 1/2 cosine 3x. And it just looks a little bit nicer to put the positive one first and the negative one second, so that minus sign is in the middle. It's not absolutely necessary, but it's always good to start learning how to have really good notation. All right, use a product to sum formula to find the exact value of cosine 75 sine 15. And so we're going to use the product to sum formula that goes with cosine sine. So cosine 75 sine 15 is equal to 1/2 times sine u plus v minus sine u minus v. And so that's 1/2 sine 90 minus sine 60. And since we know that sine 90 is 1 and sine 60 is square root of 3 over 2, we're just going to have 1/2 minus square root of 3 over 4. And if we get the common denominator, we're going to have 2 minus the square root of 3 over 4. All right, sum to product formulas. You should have known that was going to happen. So cosine x minus cosine y is equal to negative sine of the fraction x plus y over 2 and sine of the fraction x minus y over 2. So we're not going to derive those. We will just write each expression in this problem as a product. So sine 7 theta plus sine 4 theta, we're going to use that third row down on that sum to product formulas. And so we are going to have 2 times the sine of 7 theta plus 4 theta over 2 cosine 7 theta plus 4 theta over 2. So that's just 2 sine 11 theta over 2 and cosine 3 theta over 2. And then for cosine alpha minus cosine 3 alpha, we're going to use that first product formula, and we'll have negative 2 sine alpha plus 3 alpha over 2 sine alpha minus 3 alpha over 2. And so that is negative 2 sine 4 alpha over 2, which is 2 alpha, sine alpha minus 3 alpha over 2, which is negative 2 alpha over 2, which is negative alpha. And since sine is odd, we can rewrite sine negative alpha as negative sine alpha. And so that whole expression there is going to become positive. And it's going to be sine 2 alpha sine alpha. Use a sum to product formula to find the exact value of cosine 255 plus cosine 195. So cosine x plus cosine y looks like this. And so we're just going to plug it all in there. So we're going to have 2 cosine 255 plus 195 over 2, cosine 255 minus 195 over 2. And we're just going to multiply it out, add it up, divide it, all those things. 2 cosine 225, cosine 30. And we know that cosine 225 is negative square root of 2 over 2, and cosine 30 is square root of 3 over 2. So negative square root of 6 over 4, negative 2 square root of 6 over 4, and so that's just negative square root of 6 over 2. All right, we want to verify this identity, and so we're going to just use these sum to product formulas for sine and cosine. So sine 5x plus sine x, we're going to use this sum to product formula and plug it in. So we're going to have on top of this fraction that we're starting with, we're going to have this 2 sine 5x plus x over 2 cosine 5x minus x over 2. And now in the denominator, we're going to do cosine 5x plus cosine x. So we're going to have to use the sum to product formula for cosine, which looks like this. So we're going to have 2 cosine 5x plus x over 2 cosine 5x minus x over 2. So the 2's are going to cancel, and we're just going to have on top sine 6x over 2, which is 3x, cosine 4x over 2, which is 2x. On the bottom, we're going to have cosine 6x over 2, which is 3x, and cosine 5x minus x over 2, which is cosine 2x. And so the cosine 2x's are going to cancel, and you can see that you just have sine 3x over cosine 3x, which is tangent 3x.